Hi, this is Mr. Manley. I'm going to do a video here about geometric sequences and series. Say that we have let's take a scenario here where I'm standing here and I am, say, 10 feet from a wall. So I'm going to say this is 10 feet. And let's say I walk halfway to the wall. How far have I walked? I have walked 5 feet. And let's say I'm like right there. And then I stop. And then I walk halfway to the wall again. How far did I walk the second time? The second time I walked 2.5 feet. And I stop, and then I'm going to walk halfway again. So that time I walked 1.25 feet. Now let's say I keep moving toward the wall in this manner. Whatever distance is left, I move halfway toward the wall, stop. I move halfway toward the wall, stop. Now a question, really the big question that we have here, or that I could pose is, if I keep doing this, let's say I do this, let's say I'm going to do this 100 times, what's the total distance that I will have walked? So that's one question that we could ask. And if you think about that, I'd go half the distance, and then I'd go half that distance, and then by the time I get into here, it's getting really difficult to move half the distance toward the wall because there's just not enough room, and I can't really tell whether or not because I'm walking such a small distance or moving such a small distance, you can't really do that, right? And at some point, when I say I'm going to do half the distance again, I'm just going to graze the wall. I'm going to touch the wall. So if I said do this 100 times, I said I'm going to do it 100 times, that's really not possible to do. That wouldn't be possible to do, would it? You'd go ahead and stand 10 feet from a wall and try to walk half the distance to the wall 100 times, and you're not going to be able to do it. You're going to be able to do it like maybe 6 or 7 times. So if I look at that and I go, well, I was only able to do it 6 or 7 times. Now, if I could do it 100 times, because that's like my superpower, and I'm able to do that in some alternate universe, how far would I have walked? At some point, you're just going to have to accept that I walked 10 feet. Now, you may say that, well, you were still walking half the distance to the wall, but in reality, we're just going to give up, right? And we're going to say, okay, it's 10 feet. Fine, 10 feet. So keep that in mind. Well, we may come back to that. So that might be a little experiment to do and a little question that we could ask. But let's go ahead and try and put this in some mathematic terms. One is, let's call this each of these numbers here, 5, 2.5, 1.25. So let's call each of these numbers, say that it has a position, right? So this one is in the first position, this one is in the second position, this one is in the third position. And then based upon what I was saying, is somewhere out here I've got one that was in the 100th position. That might be an interesting next question. If I did this 100 times, how far would I have to be able to move on the 100th time? So let's do that. Let's figure that out. Okay. Now, you could pause this right now and see if you could figure that out. And I think that you probably could. Think about it. Okay, if you paused it, welcome back. I'm gonna look at the mathematic way to do this, and then maybe we'll go back and look at how someone might have actually done it. What I'm going to say is that each of these numbers, each of these is some number A. Each of the 5, 2.5, 1.25 is some number A, and then sub n, this n here is its position. And this is how I would read this. I would read it A sub, as in subscript, n. So each of these is a number, A sub n. And it is equal to, any given number is equal to the first number in the whole sequence, which is the 5. This is A sub 1 in this case, times R, a common ratio, raised to the n minus 1. Now, if I can say that I have a geometric sequence, I can use this formula. I guess we haven't really confirmed necessarily that this is a geometric sequence. So let's talk about how we look at whether or not it's a geometric sequence. We look at whether or not it's a geometric sequence by looking at what did I multiply? 5 times what to get to the second term? The first term is 5, and what did I multiply by? I went times 1/2 to get to the second term. Then I look at the next term and I say, what do I multiply to get from that term to that term? And it's 1/2. Now, when I have that, when that number shows up, the same number shows up twice for multiplying, I'm multiplying by the same thing to get to each successive number, then this is called a geometric sequence. And just to review, a sequence is a list of numbers with a pattern that has some pattern. And a series is the sum of a list of numbers, of a list that has a pattern. Okay, so I'm talking about sequence right now. I'm just talking about the list of numbers. Okay, so what do we got here? We got A sub n. We got that it's geometric. When we find this number here, this 1/2, that's called the common ratio. Common ratio, and our common ratio here is R equals 1/2. Okay, now we can fill out this formula down here, down in the bottom of the screen. A sub n equals A sub 1. So I can go A sub n is equal to A sub 1, which is 5 for this problem, or for this list of numbers, times R, which is 1/2, and then to the n minus 1. And n is the unknown, right? That n is the value that we're saying it's the variable, right? So I want n to be able to be anything. And what did I say a few minutes ago? Several minutes ago, I said, I want to know, what about when n is 100? What's the 100th term? So let's go ahead and do that. I'm going to say A sub 100 is equal to 5 times 1/2 to the 100 minus 1. And that's going to give us the value, the distance of the 100th step. Yeah? So we could look at that calculation. Even without actually putting it into a calculator, you can see that it's a little bit ridiculous, right? Can you see that if I do 1/2 to the 100 minus 1, that's 1/2 to the 99th power? So I'm going to have 5 over 2 to the 99th. Well, 2 to the 99th, that's a ridiculous number. I think most calculators, if I try and enter this into the calculator and evaluate it, the calculator is just going to come out and say 0. You might have calculators that give you something in in a scientific notation that gives you what is the tiny, tiny number that this is. But for all intents and purposes, certainly for the purposes, the practical purposes of moving toward a wall, this is 0. I cannot take a step of that distance. Now let's talk about the sum of this. We know that the sum is 10. Now you may say, I don't accept that, because at that 100th step, you still haven't gotten to the wall. And if you want to say that, then feel free. But I'm going to say that at the 100th step, I'm already at the wall. I can't move that distance anymore. There's no measuring device I have. If I have some, I don't know, maybe there's some laser device that could measure that actual distance, but there's no way I could move my foot that distance, even if there were something that could measure it. So let's look at mathematically what the total distance is. We're going to switch from a sub n to s sub n. So once we switch from a to s, we're switching from talking about a sequence to talking about a series. And if I do this, if I say s sub 100, that means I want to find the sum of the first 100 terms. Okay, there's a formula that goes along with this, s sub n. So this formula is, we see the same variables that we had with the other. So we have a sub 1, that's the first term. We have r, a couple of r's, that's the common ratio. And we have n, that's our variable. So if we want to know the sum of the first 100 terms, we just plug into that equation. And that's going to be 5 for a sub 1 times 1 minus 1/2 to the 100 over 1 minus 1/2. And that is equal to 5 over 1/2. Because look at this. This guy here, 1/2 to the 100. Again, that is so small, certainly in this context, as to be negligible. So I have 1 minus 0, essentially. So 5 times 1 minus 0 is 5 in the numerator. And in the denominator, there, we've got 1 minus 1/2, which is 1/2. So that's equal to 10, which is what we knew it was in this circumstance. Let's just look at one more thing. With this, it's really not anything different, just a little notation issue, that if I could represent this like this sum, this s sub 100 is equal to the sum, so that's a Greek letter sigma, of whatever the sequence was. So it was 5 times 1/2 to the n minus 1, and that's to 100. So this is just this is a mathy way here of writing this sum without evaluating it yet. The evaluating it is going to be, we're going to use this here to evaluate it. So this is just a notation. This is just a notation issue about how to write this using, and it's actually called sigma notation. And to do sigma notation, you're going to what are you going to do? You're going to have to know the sequence there. So what is the sequence, the a sub n? And then you're going to say you want the sum, the sigma. summing from the first term, and then this is to whatever term you're ending up with. And again, if you caught, I don't know if you caught it, but the way that I read this, I'll write it out. It is the sum of 5 times 1/2 to the n minus 1 for values of n from 1 to 100. That's how I would read that, the sigma notation there. Okay, so there's just a little introduction to geometric sequences and series. In context, I thought was an interesting way to do it. And then when we break it down into the individual problems that you would see in a text or on a worksheet, hopefully you can pull out the little pieces here, certainly for A sub n and S sub n, maybe be able to read sigma notation and use that.